The Milky Way is not a static picture but a living, breathing entity. Its true architects are colossal structures known as giant molecular clouds, cosmic titans of gas and dust that serve as both the cradle and the grave for stars. By the end of our journey, you will understand the dramatic life cycle of these clouds and how their fate is directly tied to the atoms that make up your own body. We will uncover what mysterious force can tear apart a cloud light years across, and why the chaotic birth of a star is also a death sentence for its nursery. What does the constant churn of these celestial giants reveal about our own place in the cosmos? These vast clouds are the fundamental reservoirs of the galaxy's raw material. To truly comprehend their existence, we must first understand their staggering scale and substance. A single giant molecular cloud can span over 100 light-years from end to end, containing enough mass to forge hundreds of thousands of stars like our own Sun. Within their dark, frigid hearts, temperatures plunge to just a dozen degrees above absolute zero. This profound cold is not an emptiness, but a necessity. It creates a dense, protective shroud that blocks the destructive power of external starlight, allowing fragile molecular bonds to form and survive. The primary ingredient is molecular hydrogen, two hydrogen atoms linked together, which makes up the overwhelming bulk of the cloud. Mixed within this hydrogen gas are fine grains of interstellar dust, tiny particles of carbon and silicate, similar to soot or sand. These dust grains are far more than just cosmic dirt. They serve as a crucial catalyst. Their surfaces provide a solid platform where hydrogen atoms can meet, stick, and pair up to form the very molecules that give these clouds their name. This delicate balance of cold, darkness, and dust creates the only known environments in the galaxy where the profound and beautiful process of star birth can begin. Yet within this cosmic deep freeze, a surprisingly complex chemical soup is brewing. While molecular hydrogen provides the bulk of the material, it is the trace ingredients that truly bring these clouds to life. Tiny grains of interstellar dust, each one smaller than a particle of smoke, are the unsung heroes of this story. They act as miniature refrigerators, efficiently radiating the cloud's faint heat out into space. This constant cooling is vital, as it allows the immense pull of gravity to overcome the gas's internal pressure, initiating the slow, inexorable collapse of the entire structure. But these dust grains are more than just cooling agents. They are also cosmic factories. On their frigid surfaces, individual atoms meet and stick, engaging in a silent, slow-motion dance that forges molecules far more complex than simple hydrogen. Water, ammonia, and even rudimentary organic molecules begin to coat these microscopic specks. These are the very precursors to the chemistry of life itself, born in the dark between the stars. This rich molecular tapestry does not sit idly by. It actively participates in the cloud's destiny. Different molecules absorb and release energy in unique ways, directly influencing the local temperature and pressure, and therefore the cloud's ability to birth new stars. The incredible chemical diversity found within a single cloud is a direct reflection of its turbulent and dynamic heart. All of this intricate chemistry sets the stage for the immense physical forces that will soon tear the cloud apart. These dark, cold cores are where the galaxy itself learns to shine. Deep within the cloud's protective shroud, gravity begins its quiet, relentless work. A pocket of gas just slightly denser than its surroundings feels a stronger pull inward. It starts to contract, a process that is anything but peaceful. This is a violent, competitive struggle for survival on a cosmic scale. As a knot of gas collapses, it grows hotter and denser, pulling in more material from the surrounding fog with ever-increasing hunger. These nascent objects, known as protostars, are the fiery embryos of future suns. A single giant molecular cloud can be a frenzied maternity ward, giving birth to thousands of stars at once. The stellar family produced is incredibly diverse, ranging from long-lived, diminutive red dwarfs to brilliant, massive O-type stars that blaze with the power of millions of our suns, destined to live fast and die young. We can even see a nearby example with our own eyes, the beautiful Orion Nebula, that glowing sword in the constellation's belt, is not the cloud itself. It is merely a small, illuminated cavity, a blister on the surface of the vast, dark Orion molecular cloud. The intense light from a handful of newborn stars within is burning away their own natal cocoon, a breathtaking preview of the paradox to come. For the very act of creation, the glorious birth of stars, is also the beginning of the end for the cloud that nurtured them. These newborn stars carry a terrible contradiction within their brilliant hearts. The most massive stars are especially destructive, acting like cosmic tyrants that dominate their surroundings. They flood their nursery with intense ultraviolet radiation, a powerful energy that strikes the surrounding hydrogen gas and tears electrons from their atoms. This process, called ionization, violently heats the gas, causing it to glow and expand with immense pressure. At the same time, these stars unleash torrents of charged particles, stellar winds that rush outward like a relentless hurricane. Together, this radiation and these winds carve out vast cavities within the cloud, pushing the remaining gas and dust into dense, compressed shells. This self-inflicted violence is known to astronomers as feedback, a fundamental force that governs the galaxy itself. Feedback erodes the cloud from the inside out, evaporating the reservoir of raw material and halting the birth of new stars. Yet in its destructive wake, it also sows the seeds for future creation. The very shells of gas pushed aside by these expanding bubbles can become so dense that they themselves collapse under gravity, triggering a second generation of star formation at the cloud's edges. This feedback loop is a key regulator, a cosmic balancing act that ensures a galaxy does not burn through all its star-forming fuel in a single, frantic burst. The cloud is locked in a constant struggle, caught between the inward crush of gravity and the outward fury of its own stellar children. But this internal drama is only half the story, as even greater forces are at work from the outside. While the internal rebellion of newborn stars tears at a cloud from within, the galaxy itself exerts its own immense and impersonal forces. The majestic spiral arms we see in pictures are not static structures, but great waves of compression rolling through the galactic disk. When a giant molecular cloud enters one of these spiral arms, it is like a ship sailing into a cosmic storm front. The cloud is suddenly squeezed, its gas compressed to much higher densities. This violent compression can be the final push needed to tip the balance, triggering the gravitational collapse of vast gas reservoirs and igniting a firestorm of new star formation. This is how the galaxy orchestrates its grandest stellar nurseries, marking a dramatic new chapter in a cloud's life. Yet, the galaxy also holds a destructive tool. The Milky Way does not spin like a solid wheel. Its inner regions orbit the galactic center much faster than the outer ones. This differential rotation creates a powerful shearing force, an invisible current that stretches a cloud over millions of years, pulling it apart like cosmic taffy. A cloud's entire existence becomes a relentless tug of war. Its own self-gravity acts as an anchor, desperately trying to hold its form, while the galactic shear works tirelessly to shred it into a diffuse stream. Where a cloud lives in the galaxy dictates its fate. Those born in the chaotic environment of a spiral arm may live fast and die young in a blaze of stellar glory, while clouds in the quieter outskirts might persist for much longer, slowly succumbing to the patient pull of shear. This galactic context is the ultimate author of a cloud story, writing a diverse library of lifetimes and behaviors across the Milky Way. So how long does a celestial giant actually get to live? The clock is ticking from the moment a giant molecular cloud begins to form stars, and the answer is startlingly brief. On the grand cosmic calendar, these vast structures are not enduring monuments but fleeting spectacles. The entire life cycle of a typical cloud, from its star-forming infancy to its final dispersal, spans a mere 10 to 30 million years. To put that in perspective, it is a lifespan shorter than the time since the first ancestors of modern humans appeared on Earth. This ephemeral existence is a direct and violent consequence of the very stars it creates. The most massive stars burn through their fuel in only a few million years, and their explosive feedback acts with ruthless efficiency. They simply do not permit their nursery to stand for long. The death of a cloud is rarely a single cataclysm, but a gradual unraveling. Its gas is steadily converted into new stars, blown back into the void by relentless stellar winds, or simply heated and dispersed until it can no longer hold its form. This rapid turnover reveals a profound truth about our galaxy. The beautiful, serene disk of the Milky Way is not a placid pool, but a churning, bubbling cauldron. Material is constantly being gathered, forged into stars, and then scattered back into the galaxy, only to one day be gathered again. The very atoms that once resided in a long-vanished cloud are now part of new stars, planets, and perhaps of us. This staggering variety means no two clouds share the same fate. Drifting through the galactic suburbs, the Taurus molecular cloud is a quiet, sprawling complex. It forms stars slowly and in isolation, birthing gentle, sun-like stars one by one, like a peaceful village raising its children. Yet journey to the chaotic core of the Milky Way, and you encounter a behemoth like Sagittarius B2. This cloud exists in a state of perpetual frenzy, a dense, tumultuous metropolis where gravity works overtime to forge immense star clusters in frantic, crowded bursts. The very architecture of these clouds reveals their nature. Peering inside with radio telescopes, astronomers see not simple blobs but intricate, filamentary webs. Dense strands of gas and dust, light years long, crisscross the void like cosmic rivers, with the densest knots, the future stellar nurseries, glowing at their intersections like bustling cities on a map of light. This fractal structure is a universal signature, a testament to the turbulent forces that sculpt all molecular clouds. A cloud's entire history is written in this internal tapestry. Its initial mass, the shockwaves from nearby supernova it has absorbed, and the relentless feedback from its own stellar offspring all leave their mark, determining whether it will be a quiet Taurus or a furious Sagittarius. This incredible diversity forces us to ask a deeper question. What are the fundamental rules that dictate how these chaotic, filamentary structures move and evolve from within? The word turbulent is a precise scientific description of their internal state. Within a giant molecular cloud, the gas does not sit placidly, it churns with supersonic fury. Vast rivers of material crash into one another at speeds far exceeding the local speed of sound, creating a chaotic web of shockwaves and eddies. This internal violence is not a sign of destruction, but a form of support. On the grand scale of the entire cloud, this relentless turbulence acts like an invisible scaffold, propping the structure up against the relentless, crushing force of its own gravity. It prevents the entire cloud from collapsing into a single, monstrous star in one frantic instant. So what is the engine that drives this cosmic chaos? The sources are as varied as they are powerful. Distant supernova explosions send titanic shockwaves rippling through the galactic plane, slamming into clouds and stirring them like a spoon in a cauldron. The immense gravitational tides of the galaxy itself also stretch and compress the gas, but the most potent source of turbulence comes from within, born from the cloud's own stellar children. The fierce radiation and hurricane force winds from massive stars inject colossal energy back into their nursery, shaking the very foundations of the cloud that created them. This creates a remarkable self-regulating system. Star formation drives the turbulence that then stifles further star formation, a natural feedback loop that prevents the galaxy from exhausting its fuel supply too quickly. This chaotic energy is the master sculptor, carving the intricate filaments and dense knots that we observe. It is the fundamental reason why star formation is a slow, inefficient, and beautifully structured process, rather than a single catastrophic collapse. The great mystery then becomes, how does anything ever become stable enough within this storm to form a star at all? It is within these chaotic filaments that the quietest and most profound of transformations begins. Deep inside the densest knots of gas, known as Protostellar cores, the last pockets of stability give way to gravity's final pull. A core is like a tiny island of order within the surrounding storm, but even this island has its limits. When the core accumulates enough mass, its own self-gravity becomes overwhelming. The delicate balance is broken. The internal pressure and turbulent motions that once propped it up can no longer resist, and the entire structure begins to fall in upon itself. This is not a simple shrinking, but a violent, accelerating collapse. As the core contracts, a fundamental law of physics takes over. To conserve its angular momentum, it must spin faster and faster, much like a figure skater pulling in their arms. This rapid rotation forces the collapsing cloud to flatten into a vast, swirling disk, with a growing, hot sphere of gas accumulating at its very center. This central object is a protostar, a stellar infant still swaddled in its thick, gaseous blanket. Material from the disk spirals inward, funneling onto the protostar in epic, chaotic streams. The temperature and pressure at the very heart of this nascent sun climb to unimaginable levels. For hundreds of thousands of years, this fiery embryo grows, its heat generated not by nuclear fires but by the sheer, relentless crush of gravity. Then a critical threshold is crossed. When the core temperature soars past 10 million degrees, the atomic nuclei of hydrogen are moving so furiously that they overcome their natural repulsion and slam into one another. In that instant, nuclear fusion ignites. Hydrogen atoms are forged into helium, releasing a titanic burst of energy that floods outward, halting the gravitational collapse. A new, stable star is officially born, its internal furnace now lit for millions or even billions of years to come. The leftover swirling disk of gas and dust, the star's former cradle, is now the construction site for an entirely new chapter. It is within this disk that microscopic particles will begin to clump together, eventually building planets, asteroids, and comets. This entire majestic process turns a cold, dark, and nearly invisible pocket of gas into a brilliant, self-sustaining sun. Yet, the moment that first sustained fusion reaction flashes to life, the star immediately begins to betray its own nursery. Its newfound light and fierce stellar wind start to push back against the very cloud that created it, initiating the powerful and destructive cycle of feedback that will ultimately seal the cloud's fate. From the chaotic collapse within a cloud, a stellar society emerges, complete with its own strict hierarchy. A single giant molecular cloud does not simply manufacture identical suns. It produces a full spectrum of cosmic citizens, from brilliant, short-lived titans to countless dim, long-lived red dwarfs. This initial distribution of stellar masses is so predictable it has a formal name, the initial mass function. It is a pattern repeated with stunning consistency from one end of the galaxy to the other. Why this particular pattern emerges from the turbulent chaos of a collapsing cloud is one of the great unsolved puzzles in modern astronomy. The answer seems to lie in the complex interplay of several powerful forces. The cloud's internal turbulence carves it into a web of dense filaments and knots. Within these structures, a ruthless competition begins. Protostars, the stellar embryos, all vie for the same reservoir of gas in a process called competitive accretion. Some of these embryos, often those born in the densest central hubs, manage to gravitationally attract and consume far more material than their siblings. They grow fat and powerful, rapidly becoming the massive stars of the family. Meanwhile, other protostars in less dense regions accumulate mass slowly, destined for a quieter life. Some are even violently ejected from their birth clusters by gravitational interactions, cast out into the darkness before they can gather more material, forever stunting their growth into faint brown dwarfs. This established hierarchy is not merely a curiosity, it is the central plot point in the cloud's own story. The most massive stars, though incredibly rare, wield an outsized influence. Their fierce radiation and powerful winds act as the primary engines of feedback, shaping the cloud's future and ultimately triggering its dissolution. The existence of these stellar heavyweights directly leads to the most dramatic and transformative phases of a cloud's life. The most massive stellar giants unleash a form of feedback so potent it can reshape their entire galactic neighborhood. O and B-type stars are the true titans of this process, radiating immense floods of high-energy ultraviolet light. Each photon carries enough power to violently tear electrons away from the hydrogen atoms that form the cloud's very substance. This act of ionization creates a blistering sphere of superheated, electrically charged gas, a structure astronomers call an H2 region. The pressure inside this expanding bubble of hot plasma is colossal, driving a relentless shockwave ahead of it like a plow through cosmic soil. This shockwave slams into the surrounding cold molecular gas with incredible force. In its wake, some gas is compressed into new, dense knots that will themselves collapse to form the next generation of stars. Other regions of the cloud are simply shredded and blown away, their material scattered back into the galactic void. We can witness this beautiful destruction in the iconic pillars of creation. Those towering columns of dust are not monuments of permanence, but fleeting sculptures. They are being actively evaporated by the invisible torrent of radiation from brilliant young stars just outside our view, their forms constantly reshaped by the very light that makes them visible to us. This radiative feedback is the primary force carving the cloud's final architecture, a paradoxical cycle where stellar birth fuels both further creation and total dissolution. The most dramatic chapters of this story, however, are reserved for the final, explosive acts of these massive stars. While radiation carves the cloud with light, a more physical force is also at work. The surfaces of massive stars are cauldrons of ferocious activity, and they hurl their own substance outward in a relentless gale. These stellar winds are not a gentle breeze, but a supersonic river of charged particles racing into space at millions of kilometers per hour. When this invisible hurricane slams into the slower moving gas of the surrounding cloud, the effect is explosive. It creates a violent shock front, a wall of immense pressure that superheats the gas and crushes it into dense, glowing shells. This is mechanical feedback, a brute force sculpting of the cosmic landscape. The energy transferred is staggering, further churning the cloud's internal chaos and helping to blow vast cavities clear of star-forming material. But the winds from massive stars are not the only source of this turmoil. Even a young, sun-like star, still gathering mass from its disk, experiences a paradoxical violent birth. As material spirals inward, a portion of it is channeled by powerful magnetic fields and blasted back into space. These are bipolar outflows, two incredibly focused jets of gas shooting from the star's poles in opposite directions, piercing the darkness for light years. These jets act as a vital pressure release valve for the stellar infant. They carry away excess spin or angular momentum that would otherwise prevent material from falling onto the star. Without these precise, high-energy jets, many stars would never be able to grow to their final mass. In their wake, they leave behind elongated cavities and inject more turbulence into the nursery, stirring the pot even more. Together, the broad, crushing winds of massive stars and the pinpoint precision of protostellar jets deliver a 1-2 punch of mechanical disruption. They work in concert with the erosive power of radiation to systematically dismantle the cloud that gave them life, ensuring that no stellar nursery survives the brilliant, turbulent childhood of its own creations. But the ultimate act of feedback is reserved for a star's final, explosive death. For the most massive stellar giants, their life concludes not with a quiet fade, but with a cataclysm that echoes across light years. A supernova explosion is one of the most violent events in the universe. In a matter of seconds, a dying star can unleash more energy than our own sun will produce over its entire 10 billion-year lifespan. The star's outer layers are blasted outward at speeds approaching 1/10 of the speed of light, a shock wave of unimaginable force that slams into the remains of its natal cloud. This is the final, decisive blow for a structure already weakened by radiation and stellar winds. The supernova's expanding remnant acts like a cosmic bulldozer, plowing through the cloud's shredded gas and sweeping it up into a glowing, expanding shell. This violent dispersal is not a meaningless end, but a crucial act of galactic recycling. Within that cataclysmic fire, the star forges the universe's heaviest elements. Atoms of iron, oxygen, silicon, and carbon, forged in the star's final moments, are scattered far and wide. These elements, the very stuff of rocks and air and life, are seeded into the interstellar medium, enriching the raw material for the next cycle of creation. The cloud's coherent existence is over, its identity erased as its substance is returned to the galactic pool. This explosive demise completes a grand cycle. From a cold, dark cloud, stars are born. Those stars live, shape their nursery, and then die, scattering the elements of life back into the void. The death of one cloud becomes the raw potential for countless future stars, planets, and perhaps one day new life. The death of a cloud is not a final ending, but a transformation. The very material that was once blasted apart by supernova and stellar winds begins a slow, cosmic migration. This ejected gas and dust, now enriched with heavy elements, mixes with the thin, pervasive fog of the interstellar medium. It is a galactic graveyard that is also a nursery, holding the raw ingredients for everything to come. For millions of years, this scattered material drifts, gradually cooling and losing the fierce heat of its explosive birth, but this quiet phase cannot last. The galaxy is alive with motion, and great forces are always at work. A passing spiral density wave, one of the galaxy's majestic arms, can sweep through this diffuse material like a plow, piling it up into a massive, dense wall. Alternatively, a shock wave from a distant, unrelated supernova can slam into a quiet region of gas, compressing it violently and triggering its collapse. Under these immense pressures, a miraculous shift occurs. The turbulent energy that once kept the gas diffuse is now overwhelmed by the attractive force of gravity. Individual atoms begin to clump together, and over vast timescales, these clumps attract more and more material. What was once a dispersed, invisible mist slowly coalesces into a new, coherent structure, a nascent giant molecular cloud. This new cloud is fundamentally different from its predecessor. It carries within it a legacy of past stellar generations, a chemical inheritance of heavier elements like carbon, oxygen, and iron. These atoms, forged in the hearts of long-dead stars, are the very building blocks of rocky planets and the complex chemistry that leads to life. Our own solar system is a direct product of this magnificent cycle. Every atom of iron in your blood, every atom of oxygen you breathe, was once part of a giant molecular cloud that lived and died long before our sun was even a glimmer in the galaxy's eye. This cyclical view transforms the Milky Way from a simple collection of stars into a dynamic, breathing entity, a vast engine of perpetual renewal. The efficiency of this grand cycle, how quickly and effectively a galaxy can gather its scattered ashes to build anew, is what ultimately dictates its vitality, shaping the rate at which new stars and new worlds are born across cosmic time. But how can we possibly study these dark, cosmic giants if they are so effective at hiding their own existence? The very nature of giant molecular clouds makes them ghostly phantoms in the night sky, completely invisible to the human eye and to traditional optical telescopes that see the same light we do. Their hearts are swathed in a deep, cold fog of dust that blocks and scatters the visible light from the stars behind and within them. To lift this veil, astronomers must become cosmic detectives, learning to see with entirely different kinds of eyes. They turn to other, more subtle forms of light that can pass through the dust or be emitted by the cold gas itself. This requires a powerful arsenal of tools designed to listen to the universe's quietest whispers. Radio telescopes are one of the most vital instruments in this search. These immense dishes do not collect light, but instead tune into the long wavelength radio waves emitted by the clouds. Within these clouds, specific molecules like carbon monoxide are constantly vibrating and rotating, and with each tiny shift, they emit a faint, precise radio signal. Carbon monoxide is particularly important because it is much easier to detect than the cloud's primary ingredient, molecular hydrogen. By mapping the glow of carbon monoxide, astronomers can trace the outline and internal structure of the entire hidden cloud, using it as a proxy to understand the distribution of the vast, invisible hydrogen reservoirs. Yet radio waves are only one part of the story. To peer even deeper into the dusty hearts of these stellar nurseries, scientists use infrared and sub-millimeter telescopes. This type of light has wavelengths long enough to slip between the dust grains like sunlight through a fog, rather than being blocked by them. Infrared observatories can see the warm glow of the dust grains themselves, heated ever so slightly by the embedded young stars. They can also directly observe those stellar infants, still cocooned in their thick, dusty blankets, whose visible light is completely trapped. Space-based telescopes like Herschel have been revolutionary, free from the blurring effect of Earth's atmosphere. They have provided breathtakingly detailed maps of the cosmic landscape inside these clouds, revealing the intricate, frozen rivers of gas and the dense knots where stars are beginning to form. Each of these observational techniques, from radio to infrared, gives us a different piece of the puzzle. A radio map shows the total extent of the cold gas. An infrared image reveals the hidden stellar population, and a sub-millimeter view charts the frigid dust. It is only by combining all these different views, by constructing a multi-wavelength portrait, that we can begin to understand the full, dynamic life of a giant molecular cloud. This ability to see the unseeable has transformed these cosmic phantoms into detailed, three-dimensional structures, allowing us to witness their birth, their turbulent lives, and their eventual dispersal in stunning, unprecedented detail. Yet another invisible force is at work deep within these churning clouds. Woven throughout the cosmic fog is a pervasive web of magnetic fields, an unseen skeleton that provides crucial support. These fields are not generated by the cloud itself, but are fossilized remnants of the galaxy's own magnetic field, trapped and amplified as the cloud coalesces from the interstellar medium. Imagine these lines of magnetic force as countless, invisible threads running through the gas, creating a subtle but resilient structure. This magnetic framework acts like a cosmic scaffold, propping up the cloud and providing an additional force to resist the relentless inward pull of gravity. It does not stop collapse, but it guides and channels it, shaping the chaotic flows of gas and even dictating the direction of the powerful jets that erupt from newborn stars. These fields leave a faint but detectable signature. The tiny, needle-like dust grains within the cloud slowly align themselves perpendicular to the magnetic field lines. When starlight passes through, these aligned grains polarize the light, twisting it in a specific direction. By carefully measuring this polarization, astronomers can essentially trace the invisible magnetic blueprint of the entire cloud, mapping forces that would otherwise remain completely hidden. A great mystery, however, remains. Are these magnetic fields a dominant pillar of support, or are they a minor player, easily overwhelmed by the cloud's rampant turbulence? This question is at the heart of modern star formation research. The answer will define the very initial conditions for collapse, determining how a cloud fragments and ultimately what kinds of stellar families it can produce. The final architecture of a star system, from its planets to its very composition, may be written in this invisible magnetic script from the very beginning. These invisible forces of turbulence and magnetism create a puzzle far too complex to solve with equations on a page. To truly grasp the life of a giant molecular cloud, we must build one from scratch inside a computer. Astronomers craft vast digital universes where every law of physics is translated into code. Gravity, the pull that collapses the gas; hydrodynamics, the flow of that gas as it crashes into itself. Magnetic fields, the invisible threads weaving through the chaos; radiation, the fierce light from newborn stars; and even complex chemistry, the formation of molecules on dust grains. All of these elements are set into motion simultaneously, interacting in a breathtakingly complex digital dance. The goal is deceptively simple: to start with a virtual cloud of gas and watch what happens over millions of years. Can this simulated universe produce the intricate filaments and stellar clusters we see through our telescopes? The results are nothing short of spectacular. These simulations reveal how random motions in the gas can self-organize, weaving together to form the very cosmic webs that are the hallmark of real molecular clouds. They show us how a shock wave from a supernova, modeled as a single pulse of energy, can ripple through the digital gas and trigger the birth of an entire stellar family. Scientists use these virtual laboratories to run experiments that are impossible in the real world. What happens if we turn off the magnetic fields? The cloud collapses too quickly, forming stars in a frantic, inefficient burst. What if we remove stellar feedback? The cloud is devoured entirely, leaving behind a single, monstrous star that should not exist. By comparing these alternate realities with actual telescope data, we can isolate the most crucial ingredients. The simulations strongly suggest that it is the combination of all these forces, a constant tug of war between turbulence, gravity, magnetism, and feedback, that gives rise to the universal pattern of star birth we observe. This virtual exploration is our closest look at the continuous, dynamic story of these clouds, a story for which real telescopes can only ever provide frozen moments in time. Thousands of these cosmic giants drift through the spiral arms of our galaxy, a vast and diverse population constantly being born and dying. A galactic census reveals they are not scattered at random, but are meticulously organized by the grand architecture of the Milky Way. They cluster overwhelmingly within our galaxy's majestic spiral arms, those bright lanes we see in photographs, and are also arranged in a colossal ring that girdles the galactic center about 15,000 light-years out from the core. This ring is a cosmic factory floor, a zone of immense density where the raw stuff of star formation is concentrated. Through ambitious mapping projects, astronomers have catalogued these behemoths, weighing them and clocking their speeds across the void. What emerges from this census is a profound stability amid constant change. While any single cloud lives a brief and turbulent life, the galactic population of clouds exists in a perfect dynamic balance. For every cloud that is shredded by its own stellar children, a new one is coalescing from the scattered remains of its predecessors elsewhere in the disk. This equilibrium means the total mass locked away in all of our galaxy's molecular clouds at any one moment is remarkably constant. That single number, that reservoir of cold gas, is the ultimate throttle on the Milky Way's engine of creation. It directly dictates how many new stars our galaxy can birth each year. By studying this population as a whole, we gain a global diagnosis of our galaxy's health and its current evolutionary phase. This sweeping perspective does more than just tell us about our own celestial home. It gives us a universal ruler. We can look out at other galaxies, see the glow of their own molecular gas, and understand their place in the grand cycle of cosmic life and renewal. The story of these clouds does not end at the Milky Way's edge. To truly grasp their nature, we must look beyond our own galaxy, into the vast diversity of the cosmos. In the chaotic, formless, irregular galaxies, star formation is a scattered and solitary affair. Here, giant molecular clouds often exist in relative isolation, lacking the powerful compression of spiral arms. Their star birth may be sparked by quieter, more random events, like a chance collision with another cloud, creating a stellar nursery far from any galactic metropolis. This stands in stark contrast to the frenzied cores of starburst galaxies. In these cosmic powerhouses, star formation rages at a rate hundreds of times faster than in our own Milky Way. The clouds here are colossal, under immense pressure, and caught in a self-destructive feedback loop of unimaginable intensity. They are simultaneously creating and being obliterated by waves of brilliant, massive stars, turning entire regions into a blaze of simultaneous creation and ruin. We can now witness this galactic drama in stunning detail. Powerful observatories like the Atacama Large Millimeter/Submillimeter Array, a vast collection of radio antennas high in the Chilean desert, are acting as interstellar telescopes. They possess the resolution to pick out individual giant molecular clouds in our galactic neighbors, allowing us to compare their size, mass, and internal structure to those we know at home. This extragalactic work is the ultimate test for our theories. It asks a profound question: are the rules we have learned here universal? The answer appears to be both yes and no. The fundamental physics of gravity, turbulence, and feedback remain the same wherever you go in the universe. Gas will always collapse when gravity wins, and stars will always blow their surroundings apart. Yet, the specific outcome of this eternal struggle is exquisitely tuned by the environment. A galaxy's total mass, its elegant spiral shape or lack thereof, and a violent history of galactic mergers all impose their will on the clouds within. A cloud born in a quiet, aging galaxy will have a very different life from one forged in the chaotic aftermath of a galactic collision. This cosmic perspective does not diminish our own galaxy's story, but rather enriches it, revealing our Milky Way as one unique expression of a universal dynamic process. This staggering inefficiency is one of the cosmos's great paradoxes. A giant molecular cloud contains enough raw material to forge hundreds of thousands of suns, yet it typically converts a mere 1 to 5% of its colossal mass into stars. The vast majority of the gas, over 95%, is simply blown back into the void, wasted from the perspective of star formation. So why does the universe operate with such apparent extravagance? The answer is a delicate and relentless balancing act. On one side, you have the inward crush of gravity, the force that wants to pull every last atom into a new star. Pushing back with immense strength are the supporting forces of supersonic turbulence and magnetic fields. Think of a cloud not as a placid pool, but as a pot of violently boiling water. Those chaotic churning motions create an internal pressure, a form of support that acts like an invisible scaffold, preventing the vast bulk of the cloud from collapsing all at once. Gravity is forced to work in the densest, most placid knots where this turbulent energy has been able to dissipate. This is why star formation is a slow, piecemeal process, and not a single, catastrophic collapse of the entire structure. But just as the cloud begins to form stars, a new and even more powerful regulatory force awakens. The most massive stars that are born act as cosmic saboteurs. Their intense radiation and hurricane-force winds blast through the nursery, violently heating and dispersing the very gas that could have formed their stellar siblings. This feedback is ruthlessly efficient, like a forest fire that clears the land but also prevents new saplings from growing too densely. This low efficiency is not a flaw in the design, it is a vital feature of a healthy galaxy. If clouds were even slightly more efficient, converting say 30 or 40% of their mass into stars, the consequences would be dramatic and brief. Galaxies would burn through their entire reservoir of star-forming fuel in a single, frantic burst of creation. The universe would be filled with galaxies that flared into brilliance and then faded into cosmic stagnation, their star-forming engines dead. There would be no long, steady evolution, no gradual enrichment of elements, and likely no stable planetary systems like our own. The fact that star formation is so inefficient is what allows galaxies to have long, productive lives, slowly turning their gas into stars over billions of years. Unraveling the precise balance of this cosmic throttle, how turbulence, magnetism, and feedback all intertwine to set that crucial 1 to 5% figure, remains one of the most active and challenging pursuits in modern astrophysics. It requires stitching together every thread of the cloud story into a single, coherent picture of regulated creation. The same dust grains that once helped a cold cloud collapse are the very seeds of planets. Within the frigid darkness of a giant molecular cloud, those microscopic particles of carbon and silicate become coated in a frozen mantle of water ice and complex organic molecules. This rich chemical inheritance is not lost when a star ignites. Instead, it is swept up into the swirling protoplanetary disk that forms around the newborn sun, a vast, flat arena where the next act of cosmic construction begins. Here in that disk, the dust grains begin to stick together, colliding gently to form ever larger pebbles and rocks. Over millions of years, this process of gentle accumulation snowballs, creating kilometer-sized planetesimals that then gravitationally attract one another, assembling the cores of future worlds. The specific recipe of the original cloud dictates what kind of planets are on the menu. A cloud rich in gas and dust might readily form the massive cores that quickly accrete vast hydrogen atmospheres, becoming gas giants like Jupiter. A cloud with a different balance of elements might favor the formation of smaller, rockier bodies. Our own solar system is a direct product of such a specific chemical legacy. Every element on Earth heavier than hydrogen and helium, from the iron in our planet's core to the calcium in our bones, was forged in the heart of a long-dead star and then delivered to our natal cloud before the Sun even existed. This means the specific giant molecular cloud our solar system was born from over 4.6 billion years ago was already pre-enriched with the essential ingredients for rocky planets and for life itself. The journey from a cold, dark cloud to a warm, watery world is a direct and unbroken chain. The water in your glass, the carbon in your cells, all were once part of the intricate chemistry taking place on the surface of a speck of dust drifting between the stars. Understanding the turbulent lives of these clouds is therefore not just about mapping the birth of stars, but about tracing our own deepest cosmic ancestry. Our own solar system is currently sailing through the ghost of a long-dead giant. We are residents of the local interstellar cloud, a faint and wispy bubble of gas, a sparse remnant of colossal molecular clouds that lived and died eons ago. This is our immediate galactic environment, a sample of the recycled material our models describe. In just 10,000 to 20,000 years, a blink in cosmic time, the Sun's motion will carry us out of this cloud and into a neighboring region of space. The interstellar medium there could be slightly denser or perhaps more rarefied, with a different configuration of magnetic fields woven through it. For those of us on Earth, this transition will be completely unnoticeable, our atmosphere and magnetic field providing a perfect shield, but its significance is profound. It is a quiet demonstration that we are not separate from the grand cycle we have been exploring. Our solar system is a traveler, moving through the ever-shifting landscape of the galaxy, a landscape built from the ashes of stellar generations past. The very atoms that make up the air we breathe are, at this very moment, part of this gentle interstellar flow. This ongoing journey connects us directly to the turbulent lives and transformative deaths of the celestial giants that came before, a constant reminder that our local space is a temporary and ever-changing sample of the galaxy's eternal process of renewal. This universal stellar census is a profound cosmic puzzle. Across our galaxy and even in galaxies millions of light-years away, the distribution of newborn stars follows a consistent, predictable pattern. For every single brilliant, massive star born, a cloud will produce roughly 10 stars of half that mass and 100 stars of a quarter the mass. This statistical rule, known as the initial mass function, is nature's seemingly default setting for building stellar families. Why this particular pattern emerges from the chaotic turbulence of different clouds is a mystery that challenges our deepest understanding. The conditions within a star-forming cloud are anything but uniform. One cloud might be a raging storm of supersonic motions, while another is a quieter, more magnetically dominated structure. If the initial setup varies so dramatically, why does the final stellar output look so eerily similar? Does this imply that a single, dominant physical process is at work, a universal governor that overrides local conditions? Or is it the result of a complex, self-regulating dance where multiple competing processes, turbulence, gravity, and feedback, always manage to cancel each other out, arriving at the same average result no matter how they begin? Solving this riddle is not just an academic exercise, it gets to the very heart of how the universe operates. The distribution of stellar masses dictates everything that follows. The number of luminous giants determines the intensity of a cloud's feedback and its eventual dispersal. The abundance of long-lived, smaller stars defines the long-term light and chemical evolution of a galaxy. And the population of stable, sun-like stars directly influences the number of potential worlds that could harbor life. If this initial mass function were even slightly different, the cosmic landscape would be unrecognizable. Researchers are now using incredibly detailed computer simulations to test these ideas, creating virtual clouds with slightly altered laws to see which ones reproduce the universal population we observe. The answer will reveal whether the star formation process is governed by a simple, fundamental law we have yet to discover, or if it is a magnificent example of emergent complexity, where chaos and order conspire to create a familiar pattern across the vast expanse of the cosmos. But this vital turbulence poses a deep and unresolved puzzle. We know these clouds churn with supersonic fury, yet this chaos should naturally fade away, dissipating into a quiet calm in less than a single crossing time of the cloud itself. Since the clouds we observe are clearly in a state of constant upheaval, a continuous and powerful energy source must be acting like a giant invisible spoon, relentlessly stirring the cosmic pot to keep it from settling. So where does all this energy come from? The suspects are numerous, operating on vastly different scales. From outside the cloud, titanic shockwaves from distant supernova explosions slam into the gaseous structures, injecting energy on a colossal scale. This is a galactic scale driving mechanism, a reminder that a cloud's life is not isolated but is part of a much larger, more violent ecosystem. Yet powerful forces are also at work from within the cloud's own heart. The fierce protostellar jets that erupt from newborn stars and the relentless stellar winds from massive O-type stars act as internal engines, pumping energy directly back into their nursery. The great mystery is one of balance. Is one of these sources dominant, or is it the combined, chaotic chorus of all of them that maintains the observed levels of turbulence? This is not merely an academic question. The answer directly shapes how a cloud fragments, how long it lives, and ultimately, what kind of stellar family it produces. Identifying the primary driver is essential for creating realistic models that can accurately trace a cloud's entire life story, linking the grand sweep of galactic dynamics to the pinpoint precision of a single protostar's fiery birth. The invisible force of turbulence thus connects everything, from the death rattle of a star far away to the first gentle spin of a planetary system coming into being. Deep within the cloud's dark heart, an invisible rain of cosmic particles is constantly falling. These are cosmic rays, atomic nuclei accelerated to nearly the speed of light by distant supernova and other violent cosmic events. They are not light but physical particles that can punch straight through the dense veils of dust that block even the most powerful starlight. This gives them a unique and powerful role, allowing them to reach the cloud's most secluded and frigid cores. When one of these high-energy particles strikes a molecule of hydrogen deep inside the cloud, it can rip away an electron, creating a positively charged ion. This single tiny event of ionization sets off a chain reaction. The newly formed ion is highly reactive, eagerly seeking out other molecules to bond with in the darkness. This triggers a surprisingly complex and rich network of chemical reactions, forging molecules far more intricate than the simple hydrogen that started the process. It is a form of alchemy driven by pure, high-energy impact, a hidden chemical engine that operates where the warmth of starlight can never reach. This astrochemical network may be crucial for creating the complex organic molecules, the very precursors to the chemistry of life that we find coating dust grains within these stellar nurseries. But the influence of cosmic rays extends far beyond mere chemistry. The ions they create become electrically charged, and charged particles become locked to the cloud's invisible magnetic field lines. This force acts like a subtle glue, increasing the friction between the neutral gas and the magnetic field. This coupling is a critical but poorly understood factor in controlling how the cloud resists its own gravitational collapse. A higher density of ions caused by a stronger flux of cosmic rays could allow the magnetic field to exert a firmer grip on the gas, effectively propping up the cloud and slowing down the birth of stars. Alternatively, if cosmic rays are weaker in some regions, the magnetic support might be less effective, allowing gravity to win more easily. The great mystery is that we do not know if this cosmic ray rain is a gentle, constant drizzle across the entire galaxy, or if it is a torrential downpour in some regions and a mere sprinkle in others. Could the violent death of a nearby star cluster flood a cloud with particles, dramatically altering its internal physics and chemistry? Understanding this variable is essential for building a complete picture of our cosmic origins. Every planet and every ingredient for life was assembled from material processed within these clouds. The silent, penetrating rain of cosmic rays may have been a hidden architect in that entire process, subtly shaping the conditions that led to our own existence. Our view into these cosmic nurseries is about to become clearer than ever before. A new generation of observatories is coming online, each designed to probe a different facet of the cloud's turbulent life. The James Webb Space Telescope, with its infrared eyes, peers straight through the obscuring dust of nearby stellar nurseries. It is not just seeing the young stars, but studying the very physics of their birth, analyzing the complex chemistry of the gas and ice in the disks where planets are now assembling. This gives us a front-row seat to the earliest, most delicate stages of stellar infancy. Meanwhile, on the ground, the upcoming square-kilometer array represents a colossal leap in radio astronomy. This vast network of antennas will act like a single, continent-sized ear, listening to the faint radio whispers of molecules across the galaxy. It will map the distribution of cold hydrogen gas with breathtaking precision, tracing the intricate flows that simulations predict. Perhaps most importantly, it will allow us to finally chart the invisible magnetic fields that weave through these structures, measuring their strength and influence directly for the first time. These tools are not working in isolation. Advanced space telescopes and high-altitude balloon observatories complement them, creating a multi-pronged assault on the remaining mysteries. For the first time, we will be able to watch feedback in action, not as a theoretical concept, but as a real-time process, observing how a stellar wind carves a cavity or how a shockwave triggers collapse. We might even be fortunate enough to catch a giant molecular cloud in the act of being born, witnessing the slow, cosmic gathering of diffuse gas into a new celestial titan. The synergy between these powerful new eyes and our increasingly sophisticated computer simulations is creating a perfect laboratory for discovery. We are no longer just piecing together frozen moments from the past. We are preparing to watch the entire cosmic drama unfold, frame by glorious frame. Our very existence is a direct consequence of this cosmic turbulence. The chaotic lives and deaths of giant molecular clouds were not just a random spectacle, they were a carefully tuned process that made our world possible. Every parameter had to be just right. If star formation had been even slightly more efficient, the galaxy would have burned through its fuel in a frantic blaze, leaving no time for stable solar systems like ours to slowly form and mature. If the initial mass function had skewed differently, producing far more brilliant, short-lived giants, our neighborhood would have been sterilized by intense radiation. The fact that these clouds live for tens of millions of years, not mere thousands, provided the necessary window for planets to coalesce from the dusty debris. The violent feedback from massive stars, while destructive, was essential. It ensured that star formation was a regulated, gradual process, preventing the entire galactic reservoir from collapsing at once. This delicate balance created a stable, long-lived galactic environment where life could eventually emerge. The iron that carries oxygen in your blood, the calcium that strengthens your bones, and the carbon that forms the backbone of your DNA were all created in the hearts of stars that lived and died within these ancient, swirling clouds. Their explosive death seeded the interstellar medium, enriching the next generation of clouds with the very elements that make rocky planets and living organisms possible. This means you are not merely a passive observer of the cosmos. You are a living, breathing artifact of its most fundamental cycles. Your body is made from stardust, yes, but more specifically, it is assembled from the carefully processed and recycled remains of countless giant molecular clouds. This perspective weaves our own story directly into the grand tapestry of cosmic evolution, suggesting that the universe's tumultuous nature is not an obstacle to life, but its most vital prerequisite. This entire magnificent cycle is the galaxy's own heartbeat, a rhythm of creation and destruction spanning billions of years. It starts with a near void, a diffuse and scattered mist of atomic gas drifting through the spiral arms. This material slowly cools, losing the fierce heat of past stellar explosions, and begins to gather under the gentle pull of gravity and the immense pressure of passing shock waves. Over eons, this sparse fog coalesces into a new celestial titan, a giant molecular cloud. Within its dark, frigid heart, invisible forces take control. Rivaling streams of gas collide at impossible speeds, weaving a turbulent web of filaments and knots. All the while, a fossilized magnetic field, a relic from the galaxy itself, provides an unseen skeleton guiding the chaos. It is within the densest pockets of this storm that gravity finally wins its long struggle. A core collapses, spinning faster and faster, until nuclear fusion ignites and a star is born. This act of genesis, however, carries the seeds of the cloud's own demise. The most massive stars become tyrants in their nursery. Their intense radiation boils away the surrounding gas. Their hurricane force winds carve vast cavities, and their final supernova deaths deliver the decisive, explosive blow that shatters the cloud's coherence. The cloud's identity is erased, its substance now enriched with heavy elements forged in stellar furnaces and supernova blasts, is scattered back into the interstellar medium. There it will drift, cool, and wait until the galaxy's great motions gather it once again to begin the cycle anew. This is not a one-time event, but a process that has been repeating since the Milky Way was young. With each turn of this cosmic wheel, the galaxy grows richer in the elements essential for planets and life. The oxygen we breathe, the silicon in our rocks, the iron in our blood, all were built up over countless generations of these clouds. Our galaxy operates as the ultimate recycling plant, and giant molecular clouds are its most vital reactors, transforming primal hydrogen into the complex chemistry of existence. This synthesized view reveals a universe that is not static, but a beautifully self-regulating ecosystem, where the death of one generation is the raw material for the next. The turbulent life and death of giant molecular clouds is one of the great, ongoing sagas of our Milky Way. These colossal structures are far more than simple repositories of gas. They are dynamic, self-regulating engines that drive the chemical and structural evolution of our entire galaxy. From their chaotic, turbulent births to their explosive, feedback-driven deaths, they are the fundamental crucibles in which stars, planets, and the very elements of life are forged. Every twist in their story, from the invisible scaffold of magnetic fields to the relentless rain of cosmic rays, contributes to a grand, self-regulating cycle. As we continue to observe with ever more powerful tools and simulate these processes with greater fidelity, we come closer to unraveling the profound mysteries that still shroud their existence. Remember, the next time you gaze up at the starry night sky, you are witnessing the brilliant, short-lived descendants of these ancient, turbulent clouds. And you yourself are made of the material they have carefully recycled for eons, a living testament to this magnificent cosmic process. If this journey through the epic story of cosmic evolution captivated you, please subscribe for more deep dives into the mysteries of our universe. We would love to hear your thoughts on these celestial titans in the comments below.